WJEC Unit 2 Physics paper, A-level physics. This is a question about refraction where a student shines a narrow beam of light into one end of a glass block. We can see on the diagram that there's an angle of refraction in the glass of 25 degrees. First part of the question asks us to calculate the size of the angle of incidence x. So let's simply apply Snell's law. N1 sine theta 1 equals N2 sine theta 2. N1 is 1 and the angle in air is x. N2 is 1.52 and the angle in the glass is 25 degrees. Hence x is sine minus 1 of 1.52 sine 25, which gives us 40 degrees. Next we're asked to find the size of angle y. Well, it's a right angle as I've just marked. Hopefully you can see that the rest of the triangle there consists of angle y in 25 degrees. So angle y is 90, take away the 25, which is 65 degrees. Next, the question asks us to show that light doesn't refract into the air at point P. So in other words, we're looking to see whether or not total internal reflection is going to happen at P. So what we're going to do first of all is apply the critical angle formula, N1 sine theta c equals N2. The light starts in glass of refractive index 1.52. We're trying to calculate the size of theta c, and the light is trying to escape into air of refractive index 1. So theta c is sine minus 1 of 1 over 1.52, which gives us about 41 degrees. And the point here is that 65 degrees is greater than that 41 degrees, the critical angle, so total internal reflection is going to take place. And indeed that's the answer to the next part of the question. What's the full name for the process involved with a change of direction of light at point P? Simply total internal reflection. Next it asks us, how does the size of angle Z compare with the size of angle Y? Well, we should know probably from GCSE or even earlier that angle of incidence equals the angle of reflection. So both Y and Z here are equal in size. Next part of the question asks us why we have some cladding rather than just having a core with no cladding. The idea of that is that it increases the critical angle, and therefore only rays of light that are travelling close to parallel to the axis will get totally internally reflected. So this limits the paths that the light can take down the fibre, helping us to avoid multi-mode dispersion. Let me rewrite that word. So limits paths the light can take to close to the axis. That basically limits the difference in time intervals between paths of light taking the shortest and longest paths, allows the data to be transmitted at greater rates and so on. Next part, what can be said about the diameter of a monomode fibre? Well, we need to remember that monomode fibres have very small diameters. Specifically, that diameter is a few wavelengths at most. The mark scheme for this question, if you say it's a small diameter, will get you 1 mark. A few wavelengths gets you the second one. Finally, why is such a fibre called monomode? Well, the mode is basically a path that the light can take down the fibre. So this is monomode because the light can only take one path down the fibre. And that path is basically parallel to the axis. Be careful here that you don't say, for example, that the light only has one mode, because that doesn't really explain the situation. Once again, thank you for listening, and please remember to subscribe.